Hello and good day everyone. My name is Abdullah Aiman and my teammate is Muhammad Azwan. We are from Group 3. We're here to present about Superscalar out of order processor. Let's begin. Superscalar out of order processor is a type of microprocessor that can execute multiple instructions simultaneously and in an order different from the original program sequence. This is achieved through a technique called out-of-order execution, which allows the processor to identify instructions that are ready to be executed and dispatch them to available execution units, regardless of their original order. Superscalar out-of-order processors are commonly used in high-performance computing applications such as scientific simulation, financial modeling, and video game rendering. They are also used in many consumer electronic devices, such as smartphones, tablets, and laptops. Shown here is the basic architecture diagram of a superscalar out-of-order processor. We'll be explaining each of the stages. The first stage is the instruction fetch. This stage is responsible for retrieving instruction from memory. The key component of this stage includes the instruction catch, the program counter, and the branch predictor. During this stage, instructions are fetched based on the current value of the PC and predicted branch targets, placing them into the instruction buffer for decoding. The branch predictor helps improve the efficiency of this process by guessing the outcome of the branch instruction to keep the pipeline full. Next is the instruction decode. In the instruction decode stage, the fetch instructions are decoded to determine their types and operand. This stage involves components such as the instruction buffer and decode logic. The primary function of this stage is to decode the instructions to identify operations types, source and destination registers, and any immediate values. Additionally, decoding includes identifying dependencies between instructions, which is crucial for managing data hazard and ensuring correct execution order. Next is the register renaming. This stage eliminates false dependencies by mapping logical registers to physical registers. This stage involves components like the register alias table, free lists, and physical registers. During register renaming, local registers specified in instructions are mapped to available physical register to avoid write after write and write after read hazard. This process enables instruction to be executed out of order without conflicts, thus improving execution efficiency. Next is the instruction issue. The instruction issue stage selects instructions that are ready for execution and issue them to the functional units. Key component in this stage includes the issue queue and scheduler. Instructions are placed into the issue queue and the scheduler select those that are ready and dispatch them to the appropriate execution units. This stage is crucial for managing instruction dependencies and ensuring that the pipeline remains active. The execution stage is where the actual computation takes place. It involves various functional units such as ALUs, floating point units, load store units, and branch units. During this stage, instructions are executed by the functional units, performing operations such as arithmetic calculations, memory access, and branch evaluation. Executions units operate on the renamed physical registers, allowing for out-of-order execution while maintaining correct results. The memory access stage handles load and store instruction, accessing memory as needed. Component of this stage includes the data cache and load store queue. During memory access, Load instructions fetch data from memory into registers, while store instruction write data from register to memory. The load store queue manages the ordering of this memory access and handles data hazard, ensuring correct execution. In the write-back stage, the results of executed instruction are written back to the physical registers. This stage involves the write-back bus and physical register. Results from the execution unit are written back to the physical register, updating the register value with the outcome of the executed instruction. This stage ensures that the result of instruction execution are correctly recorded and made available for subsequent instructions. And lastly is the commit. The commit stage finalizes the execution of instructions by committing the result to the architectural stage in program order. Key components include the reorder buffer, architectural register. During this stage, instructions in the ROB are retired in the program order, ensuring that the architectural stage accurately reflects the correct sequence of instruction execution. This process provides precise exception handling and state recovery, maintaining the consistency and correctness of the processor's state. The register use architectural registers, which is a logical register specified in the instruction set architecture. They hold the program visible state. A physical register used during out-of-order execution. To avoid false dependencies, these registers are managed dynamically and mapped to architectural register via register renaming. Register alias table map architectural register to physical register. It is used during register renaming to track the current mapping of each logical register. Reorder buffer holds information about instructions that have been issued but not yet committed. It ensures in-order commit of instructions. Load store queue manages memory operation, ensuring correct ordering and handling dependencies between loads and stores.
Next, instruction set. First, richness. Superscalar process typically have a larger and device or set of instructions to support a wide range of operation and data type. This richness allows the compiler to generate efficient code that can be easily exploited by the processor or the execute capability, optimize performing and resource utilization. And second, orthogonality. Instructions are designed to be independent of each other and much as possible with minimal restriction on how they can be combined. This can make it easier for the processor to identify which instruction can be executed concurrently, enhance parallelism and efficiency. Third, regularity. Instructions tend to have a consistent format and operand type. This consistency simplifies and decoding and execute process, allowing the process to quickly identify dependency between instructions and assign them to operative function unit, symlink and execute pipeline. Fourth, completeness. The instruction set should be provide enough instruction to perform all the necessary tasks without requiring complex sequence of simpler instructions. This helps to reduce the number of instructions that need to be executed, improving overall performance by minimizing instruction overhead and enhance execute speed. And last, support for circulation. The instruction set may include special instruction or feature to support circularity execute. such a branch prediction hint of conditional move instruction. This instruction help the processor to continue executing instruction even when the outcome of branch is not yet known. Leveraging speculation execute to enhance program and reduce store in the pipeline. These characteristics of instruction set in Superscalar process are crucial for achieving high performance and efficiency parallel process, enabling an execution of multiple instructions simultaneously while maintaining program correctness and openness research use case. For example, for first line is load data from memory address in the R2 to register. Second line is add 10 to the value in R1 and store the result in R3. And third line is store the value in R3 to memory address. The first instruction use register indirect address to load a value from memory. The second instruction use register direct and immediately address. Third instruction use the register direct and register indirect address. In Superscalar out of the processor, the second instruction can potentially be executed before the first completeness as long as there are no dependency between R1 and R3. However, the third instruction cannot be executed until both the first and second instruction have been complete, because it depends on the value in R3 which is produced by the second instruction. Addressing mode. First, dependency analysis. This check how easy it is to find out instructions depend on each other. For example, if two instructions use the same register, it is easy to see they depend on each other. Second, execute order. Some addressing method can create dependency that limit order execute. For example, if one instruction calculate an address that another instruction needs, the second one must wait for the first one to finish. Third, performance. Different address method can affect how fast the process works. For example, immediately address, where the data is part of the instruction, can be faster than register indirect addressing, where the data is in the memory location point to byte a register. In simple term, the way address can held in instruction can influence how easily dependencies are detected, how instructions are ordered for execution, and how quickly the processor can perform the task. For example, first line load the value at the address in R2 in R1. Second line address file to R1 and store the result in R3. And third line store the value in R3 to the address in R4. In Superscalar out of order, the instruction can potentially be executed out of order depend on the data dependencies and the availability of function unit. For example, the add instruction might be executed before the load instruction completeness, as long as R1 is not being written to by another instruction in meantime. Advantages of Superscalar out of the processor. First, higher instruction level parallels ILP. This processor can handle multiple instructions at the same time. This means more tasks get done in each clock cycle, increasing overall speed and efficiency. Second, efficiency utilization of execution unit. This process can keep in part busy by rendering Erasing instruction. Even if one task is delayed, other can proceed, making the most of the processor resource and improve performance. Third, reduction of pipeline stall. This processor can avoid getting stuck waiting for one task to finish. They can skip over delayed tasks and keep working on other tasks, which makes the whole process smoother and faster. Fourth, enhance performance of diverse workloads. This processor handle different type of tasks very well, especially complex one. They can adjust the order of the task to reduce waiting time, making them faster at processing and verifying of the tasks. And last, scalability with technology advance. As technology improvement, more powerful component can be added to the processor. This allow them to keep getting better and faster with each new generation of technology. In summary, superscalar or order processor are very good at doing many things at once, keeping all their part busy, avoid delay, handling different kind of tasks efficiently, and improving as technology advance. This make them powerful and efficiency. Disadvantage of superscalar of order processor. First, complexity. Design and verification. These processes are very complex to design and check because they use complicated technique and like dependency track and register remaining. This complexity can make them take longer to develop and can lead more design mistake. In debugging, finding and fixing problem in this complex system can be taught, or of further inspection can hide the real cause of error, making it harder and more time consuming to debug. Second, power consumption. In control logic, this Azwan can control system need to of order execution use a lot of power. This can be problem for battery power device of system they need to save energy. Circulation overheat. When the processor gets the next instruction and guesses wrong, it's a waste energy doing work that it won't be used. And third, limitation performance gains. Adding more execute unit and more complex mechanism doesn't always make the processor much faster. There are points where the making is complicated doesn't improve performance by much. Dependency bottlenecks. If the code has many dependencies between instructions, the processor might be not be able to take full advantage of its ability to execute instruction of order. This limit the performance benefit. In summary, while superscalar of order processor can be very powerful, they are also very complex and use a lot of power. In addition, there are limits to how much performance can be improved by adding more complexity, especially if the code has many dependencies. This is sample of superscalar of order processor. First, intercore processor, recent generation. Superscalar, they typically have a 4 or 8 execution unit capable of decoding and issuing multiple instructions per cycle. Out of the employ one of order execution mechanism with the larger record buffer, reservation session, and register remaining capability. Additional crucial, utilize computational branch prediction and data frenzy and speculation execution technique. For the second example, AMD Ryzen processor recent generation, superscalar, similar to Intel, the future multiple execute unit for the concurrent instruction execution. out of order, employ out of order execution with the intensive micro-op sketch and scope system accepted schedule algorithms. Additional function, implement simulation multi-reading SMT to further improvement throughput by executing multiple thread and concurrently. And last example, the ARM Cortex a series processor high performance core for Superscalar feature multiple execution pipeline for concurrent instruction execution or of the implement of all the execution with various degree of complexity depending on the specific core design. Additional feature, some high performance contract are core incorporate advanced technique like dynamic branch prediction and instruction fusion. This is a reference. That's all. Thank you for my group. Bye bye.